Welcome to this brief introduction to flood frequency analysis. First, the contents of this presentation. I will start to define what is a 100-year flood by defining some basic terms and doing some basic probability calculations. I will then show how we can estimate how large is a 100-year flood, how we select the extreme events, which extreme value distributions are used, which approaches we use to estimate the parameters of the extreme value distributions, and finally how we estimate the flood quantiles. In the end, I will show how we estimate flood sizes where we have no streamflow data, where we need to use catchment properties. Start to define some basic terms. The cumulative distribution function f is the probability that the random variable x will be equal or smaller than a specific value, small x. The annual exceedance probability is the probability that a specific value is exceeded within 1 year. And the annual exceedance probability g equals 1 minus f. The return period t is the average waiting time for extreme events to exceed a specific value. We can also calculate t as 1 over the annual exceedance probability. A t-year flood has the return period of t years. What is then a 100 years flood? We know that the annual exceedance probability of a 100-year flood is 1 over 100, that equals 0.01, which means that a 100-year flood has a 1% probability to be exceeded within 1 year. The probability to not be exceeded within 1 year is 1 minus 0.01, that equals 0.99. The probability of a 100-year flood to not be exceeded within a period of 100 years is 0.99 to the power of 100, that equals 0.366. Here we assume that the flood events are independent for each year. The probability of a 100-year flood to be exceeded at least once within a period of 100 years is then 1 minus 0.366, that equals 0.634. So if we have 100 years of data, it's a 63% probability that we have actually seen a 100-year flood in this dataset. I start to explain the annual maximum method. The selection of extremes using this approach is very simple. We select the highest flood each year. If we have, for example, 50 years of data, we get 50 flood events. The annual maximum data follows in theory a generalized extreme value distribution that has 3 parameters. A location parameter m that tells something about the flood sizes, a scale parameter alpha that tells something about the spread in the flood sizes, and a shape parameter k that tells something about the most extreme flood events. When we have the annual maximum flood data from a streamflow gauging station, our challenge is to estimate the actual values of the location, scale and shape parameters so that the GEV distribution has the best possible fit to our data. We have 4 approaches that are commonly used. The first one is the method of moments. When we calculate moments, means the mean, standard deviation and coefficient of skewness from our sample of annual maximum floods. Based on this, we get the location, scale and shape parameters of the GEV distribution. The second approach is the method of L moments. Then we estimate linear moments from the flood data. Based on this, we get the parameters of the GEV distribution. The third approach is the maximum likelihood method. Then we search for the location, scale and shape parameters that maximize the likelihood of the observed floods. The likelihood is the product of the probability density function evaluated at the observations. The fourth approach is a Bayesian method. Then we use the likelihood as defined for the maximum likelihood method, but we might add some prior knowledge about floods. This is typically restrictions on the shape parameter. And a benefit of the Bayesian method is that we get uncertainty estimates for the design floods. The recommended methods are L-moment or Bayesian approach, since they are both more robust and not too sensitive to outliers in the data. When we have estimated the parameters, we can estimate the design flood for a given return period using the specified equation here on this slide. This equation is based on inverting the equation for the GEV distribution. If you have time, you can try to derive it on your own. I will now show you an example of flood frequency analysis using streamflow data from the Bulken gauge station close to Voss in Western Norway. The upstream catchment area is a bit more than 1,000 square kilometers. The elevation ranges from 47 to 1602 meters above sea level. And about 53% of the catchment is located over the timberline. 3% is covered by forests and less than 1% is urban areas. Bulken streamflow observation started in 1892 and it is one of the longest time series we have in Norway. The figure to the left shows daily flow data with annual maximum floods indicated as red dots. The figure to the right shows the seasonality of floods. The angle indicates the season, whereas the radius indicates the flood size. The color of the dots indicate the relative contribution from snowmelt and rain to the floods. We see that snowmelt gives an important contribution to floods during the spring season, whereas rain dominates during the autumn. This figure shows the result of fitting a GeV distribution to the flood data from Bulken. The return period is shown on the x-axis on a log scale, whereas the flood size is indicated on the y-axis. We see that the difference between the different estimation methods is very small for this dataset. And the 5% credibility interval for the design floods was obtained from the Bayesian method. We see that the uncertainty in flood estimates increase with increasing return period. The reason for this uncertainty is mainly the size of the dataset. The only way to reduce this uncertainty is to increase the amount of data. The small circles show the observed floods where plotting positions are used to estimate the return period of the observations. Details about plotting positions is provided in the lecture notes. An alternative approach to analyze floods is to select independent flood peaks above a threshold. The main motivation for this is that for most catchment we will get more data and thereby reduce uncertainty when we estimate design floods. The challenge is to select a reasonable threshold and to determine which peaks are independent. The selection of a threshold is a trade-off between bias and variance in flood estimates. It should be high enough for selecting extreme floods and thereby minimize the bias in our estimates. Simultaneously, it should be low enough to increase the number of flood events, so we reduce the estimation variance. Some simple rules that can be followed. We should at least have 1.64 floods per year or 1.2 to 6 floods per year. Alternatively, we could use the mean value plus 3 times the standard deviations of the complete time series to select the threshold, or alternatively, the 98% quantile of the daily flow data. And also, I think it should be not lower than the lowest annual maximum flood. But be careful, for some catchments with one major flood event per year, typically a snow melt flood, it might be impossible to get more than one flood per year. The independence of flood peaks could be assessed by the following rule. The time interval between two independent flood peaks should be at least 3 times time to peak. Time to peak is the time interval streamflow needs to increase from a low flow to a flood peak. In this plot, we see that the peaks 2 and 3 are not independent since the time interval between them is too small. A second criterion is that the minimum flow between two peaks should be at least 2/3 of the first flood peak. In this figure, we see that the flood events 6 and 7 are not independent according to this rule. We keep the highest flood, event 7. The generalized Pareto distribution is used to model the x-axis over the threshold. This distribution has a scale parameter alpha and a shape parameter k. In addition, we need to account for the number of x-axes per year by using the Poisson distribution, with one parameter lambda, that is the average number of x-axes per year. When we have estimated the scale parameter alpha and the shape parameter k, and the average number of floods per year lambda, we can estimate the design flood using the equation shown in this slide, where U0 is the selected threshold. We use again the flood data from Bulken. A threshold at the 0.98 quantile of the daily flows was used to extract the peaks. Using the independence criterions described in a previous slide, we got 291 independent flood peaks in 123 years. This gives an average flood rate of 2.4 floods per year. This plot shows the estimated flood sizes as a function of return periods, where the Bayesian approach was used for estimating the parameters of the generalized Pareto distribution, and we use the Poisson distribution to estimate the flood rate. When we have no streamflow data available at the location where we need to estimate the design flood, we need to build our estimates on other types of data. Typically, we use catchment properties, climate, land use, physiography available at the ungauged locations. Then we need to find links between the model parameters and catchment properties. A regression type model is estimated for Norwegian catchments, and such models are available in most countries. Be aware that there are large uncertainties in such estimates. It is reasonable to assume that the 95% confidence interval has 55% of the estimated flood as a lower limit and 180% of the estimated flood as the upper limit. It is almost always better to use observed flood data if the record is long enough. The Norwegian approach for estimating design floods at ungauged location is implemented in Nevina.nve.no. It is a web-based map application where you first select a point in a river network. Secondly, the application delineates the upstream catchment boundaries based on a digital elevation model. Thereafter, the catchment characteristics are calculated based on available gridded maps. Finally, the design floods are estimated based on regression equations that use the catchment characteristics from the previous step. The results could be exported to a PDF file or a shapefile. A brief summary of this presentation. If we have streamflow data available, we have two approaches to extract extremes. The first one is the annual maximum method. The second one is the peak over threshold method. For the annual maximum method, we extract the maximum value for each year, and we use the generalized extreme distribution. Following the peak over threshold method, we select independent flood events above a threshold. We need to select a reasonable threshold. We need to be sure that the flood events are independent. We fit the generalized Pareto distribution to the excesses and a Poisson distribution to the flood rate. For both the peak over threshold method and the annual maximum method, we have four estimation methods. It's the method of moments, it's the linear moment method, it is the maximum likelihood method, and the Bayesian method. From the Bayesian method, we might also get estimates of uncertainty in the design floods. At ungauged locations, we use predefined equation based on catchment characteristics. Be aware, it's a large uncertainty in such estimates.